These are the answers to homework 5G. Problem number 1. A 0.125 gram sample of magnesium metal is added to 20 milliliters of a 1.0 molar hydrochloric acid solution in a calorimeter, and the temperature of the solution increases from 21.4 degrees Celsius to 48.9 degrees Celsius. If the mass of the solution is 20.655 grams, and the specific heat capacity of the solution is 4.184 joules per gram Celsius degree, calculate the heat of the reaction in kilojoules per mole of magnesium. In a calorimetry calculation, we actually don't calculate directly the heat of the reaction. We actually calculate the heat that the water in the calorimeter has absorbed, and that's done by multiplying the heat capacity of the water solution by its mass by its change in temperature. In this particular problem, they're given the heat capacity of the water solution as identical to the heat capacity of water. Any dilute water solution, we always assume the heat capacity of that solution is the same as that of pure water. The measured mass of the solution was 20.655 grams. And if we go final temperature minus initial temperature, we get the change in temperature, which was 27.5 Celsius degrees. The grams and the Celsius degrees cancel out, and so we're able to calculate that the water solution absorbs, because it's a positive number, 2,377 joules. Whatever the water solution is absorbed, it got that heat from the reaction, and so the heat of the reaction, Q of the reaction, will just be the opposite of that. So if we change the sign, we get a Q of the reaction as negative 2,377 joules. So that's how much heat the reaction gives off in this particular experiment. If we want it in kilojoules per mole of magnesium, we'll need to know how many moles of magnesium actually reacted. So here's the balanced equation that took place. The magnesium reacted with the hydrochloric acid to form exchange reaction magnesium chloride plus hydrogen gas. So the magnesium and hydrochloric acid react in a 1:2 ratio. Now they told you how many grams of magnesium they put into the calorimeter, but they also told you how much hydrochloric acid was used. So strictly speaking, you don't know if all the 0.125 grams of magnesium reacted away, because potentially the hydrochloric acid could be the limiting reactant. If we calculate how many moles of each of those there are, we may be able to, by inspection, determine which one is the limiting reactant. So if we want to solve for how many moles of magnesium actually were reacted, it could come from the magnesium itself. Maybe that was the limiting reactant. If I convert the grams of magnesium into moles with its molar mass, there are 0.005 moles of magnesium in the container. If we calculate how many moles of HCl there are, I would multiply its molarity times its volume. And if I do that, the liters will cancel out. I'll get moles of HCl. And this comes out 0.2. So that's 4 times bigger. So because the HCl's moles are so much larger, that means that if 0.005 moles of magnesium reacts in a 1:2 ratio, it would only react with 0.010 moles of HCl. So therefore, the magnesium actually is the limiting reactant. So we can assume the 0.125 grams of magnesium did react away completely. So now that we know that's actually true, if we want to calculate the kilojoules per mole of magnesium, it's 0.00514 moles of magnesium that were actually reacted. So I'm going to divide the heat given off by the reaction by the number of moles of magnesium that did react. And if I want to switch this into kilojoules per mole, I'll do a metric conversion, switching the joules into kilojoules, and I'll wind up getting negative 462 kilojoules released per mole of magnesium. Question number 2. Using your answer from question 1, calculate the amount of heat released or absorbed when the given amounts of magnesium metal react with excess hydrochloric acid. So now if anybody else is going to do this experiment by reacting magnesium with HCl, and they determine how much magnesium they're going to react, they can figure out theoretically how much heat should be released. It's all going to be based upon this number that we calculated in part 1, which is the amount of heat released per a specific amount of magnesium, in our case per mole. So in part A, if you're going to react 0.250 moles of magnesium, all you have to do is multiply the value we got in question number 1 by the number of moles of magnesium. That causes the moles of magnesium to cancel out. So if you are going to react 0.250 moles of magnesium, you're going to release negative 116 kilojoules worth of heat energy. It has to be. For part B, they said, what if you're going to react 4.75 grams of magnesium? Well, that number's in grams, and our little conversion factor here is kilojoules per mole. So you can quite easily convert this conversion factor from kilojoules per mole into kilojoules per gram by using magnesium's molar mass of 24.31 grams per mole. I'll multiply this by 1 mole over 24.31 grams, and I now have a new conversion factor. It's how much heat is given off per gram of magnesium. Now, all I have to do is multiply this by the number of grams of magnesium that are going to be reacting in a particular experiment. The grams cancel out, and we can predict how much heat's going to be released in this particular experiment. This we would predict to be negative 90.3 kilojoules. Number 3, the reaction between hydrochloric acid and barium hydroxide has a heat of neutralization of negative 118 kilojoules per mole of barium chloride. In a coffee cup calorimeter, 100.0 milliliters of 0.500 molar hydrochloric acid is mixed with 300 milliliters of 0.100 molar barium hydroxide, both at 25.0 degrees Celsius. After the reaction, the final mixture has a mass of 400.0 grams and a specific heat capacity of 4.184 joules per gram Celsius degree. Calculate the final temperature of the mixture. So we're trying to calculate what the water's temperature is going to be at the end, and we're going to get that by knowing how much heat is given off when this reaction occurs, and they've given it to us in a really helpful number. They've told us that negative 118 kilojoules are released per every mole of barium chloride produced. So you should be able to figure out what you're trying to do in this problem. We need to know how many moles of barium chloride were produced so I can multiply this value by that number. If I multiply them together, the moles will cancel out, and I will have calculated how much heat is released by this reaction. And if that's the heat given off by the reaction, the heat gained by the water will be the exact same number, but it'll be positive. So the first step here is to calculate the number of moles of barium chloride that are produced. If we write the balanced equation between hydrochloric acid and barium hydroxide, switching the partners, you're going to wind up getting water and barium chloride, and to balance the equation, we would need a 2 in front of the HCl and a 2 in front of the water. The initial amount of hydrochloric acid given was 100.0 milliliters of 0.500 molar solution, and the barium hydroxide was 300.0 milliliters of a 0.100 molar solution. We need for our conversion factor to solve for how many moles of barium chloride would be produced when you mix these together. And this is a limiting reactant problem because we're given amounts of 2 different reactants, so I'm going to calculate the moles of each of those. First, for the hydrochloric acid, multiplying its molarity times its volume, the liters will cancel out, and we can predict that in this calorimeter we've placed 0.0500 moles of HCl. For the barium hydroxide, I'm going to multiply its molarity times its volume. The liters are going to cancel out, and this is going to tell us how many moles of barium hydroxide we placed into this calorimeter, 0.0300. Once you know the moles of each of the reactants, you can set up an initial, change, and final mole table, and we can analyze to see which one is the limiting reactant so we can determine what's left in the container at the end of the reaction. So the initial number of moles we just calculated, 0.0500 for the hydrochloric acid, 0.0300 for the barium hydroxide. One of these has to be the limiting reactant. If the hydrochloric acid all reacts away and it reacts in a 1:2 ratio with the barium hydroxide, well, a 1:2 ratio would be 0.0500 to 0.0250. And because that's less than 0.0300, we wind up getting a positive number. We've picked the correct limiting reactant, or the correct reactant to be the limiting reactant. Now, the important number, how much barium chloride is going to be produced? Well, the barium chloride and the barium hydroxide are in a 1:1 ratio. So if we're reacting away 0.025 moles of barium hydroxide, we must be forming 0.0250 moles of barium chloride. Adding up each of the columns, we know the HCl will have all reacted away. We'll have a little bit of barium hydroxide left over, but here's our important number. We will have calculated that you have produced 0.0250 moles of barium chloride. So by knowing that, we can now take the negative 118 kilojoules per mole of barium chloride and multiply by the number of moles that are being produced. This will cause the moles of barium chloride to cancel out, so we will now exactly predict how much heat is given off or absorbed when the reaction occurs in this particular experiment. It's a negative number, that means the heat's given off, So that means it gives off 2.95 kilojoules worth of heat energy, or 2,950 joules of heat energy given off. Now, how do we get the final temperature of the water solution? All this heat from the reaction, the 2,950, was given to the water. So the water's Q value is going to be the same as the reaction's Q value, but it's going to be opposite in sign. So the Q of the solution will be the negative of the Q of the reaction. So the negative of negative 2,950 is positive 2,950. And that's how much heat the water solution must have absorbed, because it's a positive number. And that's going to be related to water's heat capacity, water's mass, and water's change in temperature. And if we want to calculate the final temperature of the solution, we have to solve first for delta T. So delta T will equal the Q of the solution divided by the heat capacity and the mass, and these numbers now are all known. The Q of the solution is the 2,950 joules. The heat capacity of the solution is taken to just be the heat capacity of water. And in the lab, you would actually have to measure the mass of the solution to do this calculation, and they said it was measured to be 400.0 grams. The joules and the grams cancel out, the Celsius degrees flip to the top, and so therefore we would predict that the temperature rise in the water would be 1.76 degrees Celsius. Now, this is the change in temperature, 1.76. That will equal final temperature minus initial temperature. And if we want the initial temperature, or rather the final temperature, we move the initial temperature to the other side. So the initial temperature of 25.0 added to the change of temperature of 1.763 will give us 26.763 as an answer. This is an addition problem. The 1.76 is accurate 2 places past the decimal point, but the 25.0 is only accurate 1 place past the decimal point. So your answer has to be rounded 1 place past the decimal point. So the final answer should be 26.8 degrees Celsius. Problem number 4. A 0.1964 gram sample of quinone is burned in a bomb calorimeter that has a heat capacity of 1.56 kilojoules per Celsius degree, and the temperature of the calorimeter rises from 21.0 degrees Celsius to 24.2 degrees Celsius. Calculate the heat of combustion of quinone in kilojoules per gram of quinone. So a bomb calorimeter is treated exactly like a coffee cup calorimeter. The heat the reaction gives off is exactly equal to the heat absorbed by the water in the bomb calorimeter. And we're going to calculate the amount of heat the water in the bomb calorimeter absorbs. The only difference is the calculation of the heat of water is not going to be heat capacity of water times mass of water times change in temperature of water. For bomb calorimeters, they multiply together the heat capacity of water times the mass of water that the bomb calorimeter can hold, and they combine those into what's called the heat capacity of the bomb calorimeter. And that number is given in the problem. It's a 1.56 kilojoules per Celsius. So I'm going to use that as my heat capacity of the bomb calorimeter. And because its units are kilojoules per Celsius, that tells you the only thing you have to multiply by is the change in temperature. So if I multiply the 1.56 kilojoules per Celsius by the change in the temperature, just subtracting final minus initial, 3.2, the Celsius degrees cancel out, and that's how I get a unit of heat energy, which is either joules or kilojoules. We don't multiply by grams here. If you were going to multiply by grams, you would need to know the mass of the water, and they don't give you the mass of the water. They tell you the mass of the quinone sample, but the Q of the water wouldn't be related to the mass of the quinone. It would be related to the mass of the water. So the mass of the water and water's heat capacity have been multiplied together and combined to make the C of the bomb, which is the 1.56. So this turns out to be 4.99 kilojoules. This is how much heat the water's absorbed because it's a positive number. Therefore, the reaction has given off that exact same amount of heat, so we just change the sign. And so the Q of the reaction is going to be the negative of 4.99, which is negative 4.99 kilojoules. To get the answer in kilojoules per gram of quinone, this actually is an easy calculation now. They told us we burn 0.1964 grams of the quinone. So we take the negative 4.99 kilojoules, divided by the 0.1964 grams. The top number is only 2 significant figures, so our answer is going to have to be rounded to 2 significant figures. So we would say that the heat of combustion of quinone is negative 25 kilojoules per gram. Problem number 5, using your answer from number 4, Calculate the amount of heat released or absorbed when the given amounts of quinone are burned. So now this is really practical now. If you want to know how much heat is given off in part A when 3.65 grams of quinone are burned, well, if you know it's 25.4 kilojoules per gram of quinone, you just multiply by how many grams of quinone are being burned, and so you can exactly predict how much heat could be released when you burn a specific sample of this chemical. It comes out negative 93 kilojoules. In B, they're asking you how much heat is released if you burn 75.0 milliliters of quinone. So that's a volume. And if we know the how much heat is released per gram, then we can actually convert this from kilojoules per gram into kilojoules per milliliter by using the density as a conversion factor. It's 1.256 grams per milliliter. So if I multiply this by the 1.256 grams per milliliter, I have now calculated how many kilojoules are released per each milliliter of quinone. So now all I have to do is multiply by the number of milliliters, and I will know how much heat is going to be given off when the 75 milliliters of quinone are burned. And this comes out negative 2,400 kilojoules, rounding the answer to the two significant figures because our original negative 25 was only two significant figures. Number 6. A bomb calorimeter with a heat capacity of 10.8 kilojoules per Celsius degree has an initial temperature of 23.32 degrees Celsius. A 1.056 gram sample of benzoic acid is combusted in the calorimeter. If the benzoic acid has a heat of combustion of negative 26.42 kilojoules per gram of benzoic acid, calculate the final temperature of the bomb calorimeter. So if we're trying to figure out what the temperature is of the water in the bomb calorimeter at the end of a reaction, we're going to get that from the heat of the reaction because they've told us when benzoic acid is burned, it releases 26.42 kilojoules per gram of benzoic acid. So with this number, all we have to do is multiply this by how many grams of benzoic acid were burned in the bomb calorimeter. So what did it say? It said 1.056 grams were burned. So canceling out the grams, we know that when we burn this amount of benzoic acid in any situation, in this case in our bomb calorimeter, it's going to release negative 27.90 kilojoules. It has to be that value. And if you know how much heat a reaction is going to release, the water in a calorimeter would have to absorb that exact amount of heat. So the Q of the water in the bomb calorimeter will be the negative of negative 27.90 kilojoules. In other words, positive 27.90 kilojoules. If that's the Q that the water absorbs, in all bomb calorimeters, the Q of the water is always equal to the bomb calorimeter's heat capacity multiplied by the change in the temperature. So to solve for the change in the temperature, we're going to divide the Q of the water by the bomb calorimeter's heat capacity. That'll be the positive 27.90 kilojoules divided by the heat capacity of the bomb calorimeter, which in this problem was given as 10.8 kilojoules per Celsius degrees. Kilojoules cancel out, Celsius degrees flip to the top, and we will have calculated the change in temperature of the water, 2.58 with the guard digit 3 degrees Celsius. If we want the final temperature, the change in temperature is final minus initial. You're just going to add the initial temperature to the change in temperature, and that will give you the final. So 23.32 degrees Celsius, our initial temperature, plus 2.583, our change in temperature, will give us 25.903. And because the 23.32 and the 2.58 are both accurate 2 places past the decimal point, our answer will be rounded 2 places past the decimal point. So you'll say your final temperature of the water in the bomb calorimeter should be 25.90 degrees Celsius. Final question number 7, have access to handout 9 because we will be using that during our next lecture.